One of the foundational aspects of understanding trigonometry is this concept known as the unit circle. It's sort of the holy grail of trigonometry. And let me give you some motivation as to why we want to understand the unit circle. It's for this reason, is that in trigonometry, most math teachers require that you know the tangent and the sine and the cosine of certain common angles. And one way to know those guys is simply to memorize them. And so a lot of times you'll see a table that looks like this with 0, 30, 45, 60, 90 degrees, and maybe even a few others, and then it will list all the sine, cosine, and tangents. And you are more than welcome to try to memorize these values. If you go to Quizlet, I'm sure there's many flashcard packs that have 45. If you want to know the sine of theta of 45 degrees, it's 1 over square root of 2 or square root of 2 over 2. And so you're more than welcome to just memorize. But I think that there's a better way, and so do most math teachers, and that's using the unit circle. We can actually reason out and derive where the values come from for the sine, cosine, and tangent for common angles. So the first thing that we got to start with is this idea of the unit circle. With the unit circle, if we have our coordinate plane, with over here is our good old x-axis, and over here is our handy-dandy fun y-axis. If we have a circle that goes around like such, oh, that's a horrible circle. If it turns out that the radius of that circle is 1, then we refer to this guy as the unit circle. So if r equals 1, this guy, let's pretty that up a little bit. There we go. If r equals 1, and we have a circle that's centered at the origin of the coordinate plane, then we have what's known as a unit circle. In other words, the radius is 1 unit. Now, why do we care? Well, let's take a look. So again, we'll start off with this idea of a circle with the center at the origin, and we'll assume that the radius of this circle is equal to 1. What we're going to do is we're going to add some fancy stuff here. We're going to go ahead and add a line, and I'm going to try to draw this line at a 30-degree angle. There we go. That's my best 30-degree angle. Hope you like it. And then I'm going to draw a line that comes down, and what you'll see is we end up with a right triangle. Got a 90-degree angle right there. So again, we're going to call this, let's see how this shows up. We're going to call this guy right here, we're going to say that is a 30-degree angle. So just work with me on this. And all we're concerned about is that angle for right now. We're not concerned about what that is. We definitely are concerned that that's a 90-degree angle. But what's interesting here is we now have this special triangle. We know that if we have 90 here and 30 here, this is a 30, 60, 90 triangle. And so there's also something else that's interesting that we know. We said the radius is 1, so we know the length of the hypotenuse. So this guy here, I'm just going to go ahead and put the number 1, if you don't mind. And I'm going to remind you guys of something. We said in the past that if we have a 30, 60, 90 triangle, this guy's 30 degrees, we said that if this is the shortest side, we'll call this let's call that length of 1. If this is the longest side, this is twice that length, so we'll call that 2. And then over here we call this side square root of 3. Again, if this is length 1, this will be length square root of 3, and this will be length 2. Now, if that's the case, this is almost exactly like this situation, except here we have a hypotenuse of length 1, and here we have a hypotenuse of length 2. We're gonna change this guy around here. I'm gonna go ahead and divide this hypotenuse by 2, and divide all the sides by 2. It turns out that the ratio of the sides in a 30, 60, 90 triangle, they're always going to be the same ratio. So if I have something where the ratio is always the same, I just made a quick little table to demonstrate the idea of ratios and how they work. If I wanted something that kept a ratio of 1 to 2 to square root of 3, I could just multiply all those guys by the same number. So 2 to 4 to 2 root 3 is exactly the same ratio of 1 to 2 to root 3. And if I did 3 to 6 to 3 root 3, these three numbers are in a 1 to 2 to square root of 3 ratio. So it turns out when I multiply all three numbers by something, I get exactly the same ratio. It turns out the same is true when I divide. If I divide all three of these by the same number, or essentially I'm just multiplying each one by 1/2, then the ratio remains the same. Now what this buys us is that if we have a triangle that has a hypotenuse of 1, it means that the short side across from the 30 degrees must be a length of 1/2. And the other side that's adjacent to the 30 degrees must be square root of 3 over 2. So if I wanted to, I could go in and write these in. This length of this side here must be square root of 3 over 2 if this is 1 and this is a 30-degree angle. And then this height right here must be 1/2. So I'm going to go ahead and write that in. So this right here is 1/2 the height from there to there. Now, this gives us a really interesting result. And the result that I'm talking about is this, is that what that means is that this point on the unit circle is at an x-coordinate of square root of 3 over 2 and a y-coordinate of 1/2. Now, what the deal is on the unit circle is that every point on the unit circle has an xy coordinate, and each of the xy coordinates are the cosine and the sine of the angle of interest. So what I'm trying to tell you is this: is that the cosine of 30 degrees is exactly square root of 3 over 2. And the sine of 30 degrees is exactly 1/2. Now, what this means is we can, by the way, there is a way to calculate these guys on a calculator. Sorry about that, just lost everything for a second. There is a way to calculate the cosine of 30 on a calculator and the sine of 30 on a calculator, and what we'll see is that if we do that, we get a similar result. The only thing is the calculator rounds. It will not give us the exact value. These guys are known as the exact value, so let's write this. These are exact values. Now, it's true if your calculator gets 0.5, these guys right here, this is an exact value. Again, that one you could probably get on the calculator as well. But this guy, the calculator can never give you this value exactly. Square root of 3 is an irrational number, has infinite number of decimal places, so we'll never get a result as exact as this. That's what the unit circle does for us. It lets us figure out cosine and sine of angles all the way around the circle, and the values that we get are exact. So that's what the unit circle buys us. Now, before we go further, I'd like it if we could verify that this is true. So let me get the calculator out real quick. So what I'm trying to say to you is that by knowing this special triangle and putting it in the unit circle and doing a little a little abracadabra on the numbers, I can get the cosine of 30 degrees exactly, and that it is square root of 3 over 2. Let's double check and see if the calculator agrees. On the calculator, I can go ahead and put in 30 degrees, and I can hit cosine. And you see we get 0.86 blah, 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 blah. And you'll notice that there's a lot of decimal places, and it's because square root of 3 is an irrational number. So we aren't going to be able to get an exact value, but remember 0.866, blah, blah, blah. Now, on my calculator, I'm going to go and do square root of 3 divided by 2. This is when I did cosine of 30. So let's do just plain old 3, and I'll take the square root of it and then divide by 2. That also equals 0.86, blah, 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 blah. So it turns out that if I do the cosine on my calculator, I get of 30 degrees, I get 0.866. If I do square root of 3 divided by 2 on my calculator, I also get 0.866. In other words, I get the cosine of 30 degrees using this fancy schmancy special triangle trick. That's what we're going to do with we're going to try to do this with a bunch of angles going all the way around the unit circle. I strongly recommend that you try this calculator exercise with your own calculator, just so you can verify that, there's nothing up my sleeves, I didn't pull a fast one on you. All right, I have a lot more to say about the unit circle, but I at least wanted to introduce you to the concept of how we can take a special triangle and use it to find the cosine and sine of various angles, and that's it. We'll use the unit circle to find exact values of the cosine and sine of various angles.